Hey everyone, and welcome back for another deep dive. Today we're going to try to tackle a question that has been bugging astronomers for forever. Why does the universe look, so similar everywhere you look? You'd think that with all that cosmic chaos from the Big Bang, things would be a lot messier.
Well, our guide for this exploration is this fascinating YouTube video is from the channel History of the Universe, titled, Why is the Universe the Same Everywhere?
Yeah, I mean, the thing is the evidence for the Big Bang is really solid. We've got that red shift of distant galaxies, which is, that stretching of light as the universe expands. And then we've got the cosmic microwave background radiation that's kind of like this really faint echo from the universe's earliest moments. Oh, yeah, like the universe's baby picture. Kind of blurry, but, still tells a story. Okay, so Big Bang check. But then the video goes into these, problems with a straightforward Big Bang, like things that don't quite add up. Like, for instance, the horizon problem. How can parts of the universe that should never have been in contact have the same temperature? It's like expecting a room with a heater in one corner to be, instantly warm everywhere.
Yeah, exactly. It just doesn't make sense in a universe that's been expanding at, a normal rate since the beginning. Even light, which moves, as fast as it does, wouldn't have had enough time to travel across the universe and even out the temperature.
Right.
And it gets weirder. There's also the flatness problem. The density of the universe seems incredibly fine-tuned to be right on the edge between expanding forever and collapsing back in on itself.
Wait, hold on. So you're saying it's like flipping a coin and having it land perfectly on its edge.
Yeah.
What are the odds of that happening in this chaotic Big Bang scenario?
Yeah, precisely. And when I first learned about this, I was like, what? It's as if the universe knew precisely how much stuff to put in to achieve this this delicate balance. It really makes you wonder if there's some deeper principle we're missing here.
Yeah, okay. I'm starting to see why these problems are such a big deal. But the video doesn't stop there. It also mentions this monopole problem. Can you break that one down for us a bit?
Sure. So theory predicts that the Big Bang should have created a whole bunch of magnetic monopoles. You can think of them kind of like magnets, with only a North Pole or only a South Pole. But we've never found a single one.
Oh, well.
Yeah.
So we've got these missing monopoles, a universe that's suspiciously flat, and in distant regions acting like they've had a cosmic coffee date to get their temperatures in sync. That's a lot of head scratching. It makes you wonder if we're missing a piece of the puzzle, right?
You got it. And that's where this idea of inflation comes in. It's like a eureka moment in the history of cosmology. In 1980, this physicist, Alan Guth, he proposed this idea of cosmic inflation. Basically, it's this incredibly rapid expansion of the universe in the tiniest fraction of a second after the Big Bang. We're talking a single red blood cell ballooning to the size of the Milky Way galaxy in the blink of an eye.
Whoa. That's not just expansion, that's a cosmic explosion. But wait, that sounds pretty wild. Does it actually hold up to scrutiny? And how does it explain those, those Big Bang problems that we were just talking about?
Well, let's start with the horizon problem. Imagine the universe right before inflation. It's super tiny, almost unimaginably small. Everything's all jumbled up in contact. Then bam, inflation hits. This tiny patch gets stretched out at this insane rate. It's blowing up a tiny, perfectly mixed droplet of paint to cover, this gigantic canvas. So that initial uniformity gets preserved, even though different regions are now super far apart.
Okay. So that would explain why, those distant parts of the universe all have the same temperature. They were once all cozy and connected before inflation flung them apart. But what about that cosmic balancing act, the flatness problem?
Well, you see, inflation smooths out any initial wrinkles in the fabric of space-time. Think of it like blowing up a balloon. When it's small, you can see all the curves and bumps, right? But as you inflate it, the surface starts to appear flatter and flatter. So in a similar way, inflation stretches out the universe so that our observable patch appears flat, even if the universe as a whole might have some curvature.
So inflation is like a cosmic iron, just smoothing out those wrinkles. But what about those elusive magnetic monopoles? How does inflation explain their absence?
So inflation dramatically increases the volume of the universe, right? It's like taking a handful of chocolate chips and mixing them into a tiny ball of dough. And then suddenly that dough expands to the size of a house. The chocolate chips are still there, but they're spread out so thinly that you'd be really hard pressed to find them.
So inflation essentially diluted the concentration of monopolies, making them incredibly rare and really difficult to detect. That's a pretty elegant solution, but it almost sounds too good to be true. Is there any actual evidence to support inflation, or is it just this fancy theoretical idea?
Well, that's the million-dollar question. While inflation neatly addresses those Big Bang problems we talked about, elegance doesn't automatically equal, truth. Scientists have been on this quest to find concrete proof. One of the most promising avenues has been looking for these specific patterns in the cosmic microwave background radiation called B-mode polarization. These patterns would be like this fingerprint left behind by the rapid expansion of inflation.
So it's like searching for the smoking gun of inflation. What's the current status of that search?
Well, there was a ton of excitement back in 2014 when scientists thought they had detected these B-mode patterns. It was hailed as this major breakthrough, but unfortunately, further analysis revealed that the signal was probably caused by cosmic dust, not inflation.
Oh, man.
Yeah, it was a setback, but it kind of highlights how difficult these observations actually are.
Okay, so it seems like the jury's still out on inflation, but are there any other potential remnants of this rapid expansion that we could look for?
Absolutely. Some models of inflation predict the existence of primordial black holes, which would formed in the incredibly dense conditions of the early universe. Others suggest that inflation could have created baby universes, entirely separate regions of space-time branching off from our own. But these remnants are also super difficult to detect, and so far the search has been inconclusive.
So on the one hand, we have this elegant theory that ties up all these loose ends, but on the other hand, we're still waiting for that definitive piece of evidence. It seems like inflation is walking this tightrope between being this brilliant solution and a potentially beautiful illusion.
You hit the nail on the head. And to add another layer of complexity, not all scientists are totally on board with inflation. In fact, the video introduces us to Paul Steinhardt. He's a physicist who was initially a proponent of inflation, but has actually become one of its most vocal critics.
Wait, seriously? A former inflation enthusiast turned critic. This is getting interesting. Okay, before we get into those critiques,
He has some pretty compelling arguments against the theory.
Oh, okay.
Which we can delve into further.
Yeah, let's do that. Let's delve in. Let's get back into it then. So this physicist, Paul Steinhardt, was once a big supporter of inflation, but now he's one of its biggest critics. So what's his main beef with it?
Well, Steinhardt argues that over time, inflation theory has become too flexible. There are now countless variations and all these adjustable parameters. It makes it, super hard to test or disprove.
So it's like trying to hit a moving target. The theory can adapt to fit almost any observation, which makes it really hard to pin down.
Exactly. And kind of ironically, Steinhardt worries that inflation might actually require the same kind of fine-tuning it was originally, supposed to solve. Remember that really delicate balance of the universe's density we talked about?
Yeah.
Well, some inflation models need very specific starting conditions to produce a universe like ours, which, begs the question, how likely were those conditions?
That's a good point. If inflation needs a lot of tweaking to actually work, is it really solving the problem or just shifting it to a different level?
Yeah, that's one of Steinhardt's main arguments. And here's where things get even wilder. Some inflation models predict not just our universe, but a vast, chaotic multiverse. Essentially, it's this infinite collection of bubble universes, each with its own set of physical laws and properties.
Hold on. A multiverse.
Yeah.
So instead of a single universe born from the Big Bang, we're talking about a cosmic foam of countless universes just constantly popping into existence.
Exactly. And while that concept is, super intriguing, Steinhardt argues that it raises a whole bunch of new problems. For example, how can we even test the multiverse idea if we can only observe our own little corner of it? It kind of pushes the boundaries of what's scientifically testable.
It's like saying there are invisible unicorns in my backyard, but you can't see or hear them, and they leave, no traces. It's a cool idea, but how can we ever confirm or refute it?
Yeah, that's the dilemma. So we have inflation. It's this elegant theory that, solves some big problems, but also introduces new ones and lacks that, definitive proof. So what are we supposed to make of all this? The video doesn't give us a clear-cut answer, which I think is good. It's more about, presenting the different sides of the debate and leaving us with the question, what if inflation?
Okay, so if we put inflation on hold for a second, what are some of the alternative explanations for the universe's uniformity that the video explores? Are there any other contenders in this cosmic beauty pageant?
Well, there are a few intriguing ideas out there. One that's been gaining some traction is the Phoenix universe model. So imagine instead of a single Big Bang, the universe goes through these cycles of expansion and contraction, like a cosmic heartbeat.
So instead of like a beginning and an end, it's more like a never-ending series of big bangs and big crunches. That's wild.
Yeah. Yeah, it is. But there are some challenges with this model, too. For one thing, it needs like a way to reset the universe's entropy or, level of disorder with each cycle. Otherwise, each new cycle would start with a more like chaotic and messed up universe than the one before it.
So it's like trying to unscramble an egg after you've like made an omelet.
Yeah.
Not an easy task.
Yeah, exactly. And that's just one hurdle these cyclic models have to overcome. But there's another, like, even more mind-bending alternative that the video mentions. The idea that our universe is actually a ripple in a higher dimensional space.
Okay, now we're getting into like serious matrix territory. So instead of a balloon expanding, our universe is more like a wave propagating through this higher dimensional ocean.
Yeah, that's the general idea. But it relies on physics that, we're still struggling to grasp. It's like trying to explain the internet to someone living in the 1800s. They just wouldn't have the conceptual framework to even understand it.
Right. So it seems like we're still a ways away from a definitive answer to the question of, why the universe looks so uniform. It's fascinating that even with all our like advancements in science, this fundamental aspect of the cosmos is still such a puzzle.
It's true. It really shows how much we still have to learn about the universe and its origins, but that's also what makes cosmology so exciting. The more we learn, the more questions we kind of uncover, and that drives us to keep searching for answers.
Yeah, it's a pretty humbling thought, For all our scientific progress, we're still like just scratching at the surface of these huge cosmic mysteries. But even without all the answers, I feel like this deep dive has given us a whole new perspective on the universe.
I agree. We started with this like seemingly simple question, why does the universe look so uniform? And we ended up on this incredible journey through the Big Bang, inflation, the multiverse, even the idea of higher dimensions. It's amazing how one question can like unravel so many possibilities.
Yeah, it really shows how interconnected everything is. Like we were talking about those tiny quantum fluctuations that got like blown up during inflation. And the video explains how those, tiny random variation became the seeds for all the large scale structure we see today. Galaxies, clusters, even those like vast cosmic voids.
It's mind-boggling, isn't it? That the universe's grand design might have originated from these like tiny quantum events in the first fraction of a second after the Big Bang. It makes you realize that even the seemingly insignificant can have these like profound consequences on a cosmic scale.
Right. It's like those little imperfections in a diamond that give it its sparkle, And speaking of perspective, the video doesn't shy away from the fact that there's no like clear winner in this cosmic debate. Inflation has its strengths, but also its weaknesses. And those alternative theories, while fascinating, also have their own set of challenges.
Yeah, that's what I appreciate about the video. It doesn't try to force a conclusion, but it presents the evidence, the arguments, the open questions, and it allows us to form our own opinions. It's like a cosmic courtroom drama with inflation on trial, and the jury's still deliberating.
And maybe that's the most important takeaway for our listeners. Whether you're team inflation, team cyclic universe, or team something we haven't even thought of yet, the point is to stay curious, keep asking questions, and be open to new ideas.
Absolutely. And you don't need a PhD in astrophysics to engage with these questions. Just look up at the night sky and let your mind wander. That sense of wonder, that desire to understand our place in the cosmos, it's something we all share.
It's true. Every time I look up at the stars, I feel this like incredible sense of awe and humility. It reminds me of how much we still have to learn and how much there is to explore.
Me too. It's a reminder that, we're part of something so much bigger than ourselves, and that our understanding of the universe is constantly evolving.
So to wrap things up, if there's one thing we hope you take away from this deep dive, it's this: never stop questioning, never stop exploring, and never lose that sense of wonder when you look up at the night sky.
Yeah, because the universe is full of mysteries, and who knows, maybe one day you'll be the one to uncover the next big breakthrough.
We'll leave you with one final thought to ponder. If inflation did happen, and our observable universe is just this like tiny bubble in this vast multiverse, what does that mean for the very nature of reality itself? It's a question that might keep you up at night. But hey, that's what makes exploring the universe so much fun. Until next time, keep looking up and keep diving.